Building a sustainable battery future begins with the raw materials. That's why we aim to secure graphite, cobalt sulphate, manganese sulphate, and lithium carbonate through processes that minimize environmental impact, respect communities, and remain resilient to global challenges. Because clean energy starts with responsible sourcing. Battery electrodes are produced from electrochemically active material, conductive carbon, binder, and additives. These powders are dry mixed, then kneaded with solvent into a paste, the so-called slurry. More solvent adjusts viscosity. Finally, the slurry is filtered to remove clumps and degassed to remove trapped air. During electrode coating, a premixed slurry is applied to a thin metal foil, the current collector. Copper is used for anodes, aluminum for cathodes. Slot dies or doctor blades spread the slurry evenly. Coating quality is critical for battery performance and thus closely monitored. After coating, the slurry must be dried to remove solvents. Proper drying ensures electrochemical performance, mechanical stability, and surface quality of the electrode. Methods include warm air ovens, laser drying, or both, chosen based on production setup, speed, and energy efficiency. During calendering, the double-sided coated electrode is compressed by heated rolls to optimize thickness, porosity, and electrode density. This compression improves adhesion, cohesiveness, particle-to-particle contact, electrical conductivity, and overall mechanical stability, enhancing the electrode's electrochemical performance. To give the electrode a three-dimensional architecture, ultra-short pulse lasers are used to create microchannels. This 3D design improves ion transport, supports faster charging, and assists with even electrolyte distribution during production and operation. It also helps optimize power delivery for high-energy batteries and extends the battery's cycle life. Die cutting is an efficient method to precisely cut the electrode roll into individual pieces of the desired shape and size. This approach uses a sharp mechanical tool for fast and repeatable cuts. The individual electrodes are now ready for the next steps. Laser cutting is an alternative method to cut the electrode roll into individual pieces of the desired shape and size. This approach offers flexibility and precision without physical contact. The individual electrodes are now ready for the next steps. Before assembling a battery, electrodes and separators must be thoroughly dried, usually carried out in special drying ovens under vacuum and defined temperature. Moisture can lead to reduced performance or lifespan and pose a safety hazard. Thus, proper drying conditions are essential for achieving high-quality batteries with long-term stability. During stacking, electrode sheets are alternatively layered to form the cell's internal structure. Accurate positioning is critical to ensure uniform performance, mechanical stability, and to prevent short circuits. After stacking, the cell is filled with electrolyte so ions can flow. Full wetting of electrodes and separators is crucial. The cell is then charged and discharged. Gases are removed, it's sealed, and ready to power your device. Computational models help us understand and optimize battery production. Based on physical equations or AI, they represent specific steps and are refined using experimental data. Once accurate, they let us test settings virtually, saving time before applying the best ones in practice. A digital battery passport is like an ID card for each battery. It stores key data on materials, manufacturing, and usage, helping improve transparency and sustainability. Mandated by the EU's Battery Regulation and Green Deal, it supports manufacturers, users, and recyclers by enabling reuse and recycling. In the BatWoMan project, we developed a battery passport that collects data throughout the product's life. Information from producers, logistics providers, and recyclers is securely exchanged via a federated data space and accessed easily through a QR code.